Hello. Today, I and my colleagues would like to introduce you to the project AVATAR, which is the acronym for a reVised database quantifying the geomorphological processes during the Anthropocene. The background of this project are actually the global atmospheric nuclear bomb tests, labeling soils and sediments of the world with radionuclides. While this labeling is well known in the Northern Hemisphere, we have much less information in the Southern Hemisphere. So the aim of our project actually is to quantify the contribution of different sources, which means different tests from different countries, in these soils and sediments in the Southern Hemisphere. We are a team of 17 researchers from France and Switzerland, and we are funded by the French National Research Agency and the Swiss National Science Foundation. Please check us out on avatarproject.net. Main aims of the AVATAR project are first to unmix the different sources in soils and sediments throughout the Southern Hemisphere regarding the different countries contributing to these nuclear weapons tests. But beyond this, we also want to use the labeling of soils and sediments with radionuclides for quantifying soil erosion.
So why do we need to quantify soil erosion? Actually, we need to quantify this process because we need to convince people that we have to protect our soils, because we need to produce food for a growing population and also to avoid the transport of contaminants towards river systems and to limit reservoir siltation across landscapes. So to quantify soil erosion, there are different techniques, and one of them is to collect sediment cores in lakes, where sediment deposits year after year, and when we can analyze the radionuclide contents in the sequence of layers. So typically we use different radionuclides, including lead-210, that falls continuously with rainfall, but we also combine this information with the one provided by another radionuclide, which is artificial, cesium-137, related to nuclear bomb tests, and which is expected to peak in 1963. This is explained by the maximum fallout due to the fact that the test ban treaty came into force the year afterwards. But what we did observe in the Southern Hemisphere, instead of this sharp peak, is a much broader peak that we attributed to the combination of the maximum fallout due to the explosions that took place before the test ban treaty came into force, and those tests conducted by the French army in the late 60s and the early 70s. But to prove this hypothesis, we need another radionuclide, which is plutonium, just because the plutonium signature of the bomb test of the different countries have different signatures. So if we look at the plutonium signatures in soils of the Southern Hemisphere, we did find different signatures depending on the latitude. So nearby the equator, we have a signature which corresponds to that expected to be related to the US or the Soviet Union dominated tests. And when we go to the south, we find a deviation from this signature towards the French expected signature at a latitude located between 20 and 45 degrees south.
So my main task in the project is to evaluate the distribution of radionuclides in the Southern Hemisphere using lake sediment cores. We use them as environmental archives to reconstruct the deposition chronology of a radioactive contaminant, the 137 cesiums. In our literature review, we looked at lake sediment publication for all countries of the Southern Hemisphere, evaluating cesium activity data. This resulted in data from 160 lakes, including lagoons and dam reservoir, from 120 publications, which is a very limited dataset compared to the Northern Hemisphere. So we have plotted the maximum level of cesium activity, which in most cases represent the period of maximum fallout dating back to the 60s and expressed as becquerel per kilogram. Each dot represents a lake sediment course. In South America, maximum cesium activity is measured between 30 to 50 degrees south latitude, and the lowest levels are measured for Brazilian coastal lakes and some lakes in the Peruvian-Bolivian Andes. In Oceania, low to intermediate cesium levels are measured, and in Africa, cesium levels are generally low, except for those close to the equator. So this work will also help us to identify where data are lacking and where we should go sampling next. For instance, you can see that there is a striking lack of data between 20 to 30 degrees south latitude. Further work. These values needs to be related to lake sedimentation parameters such as the sedimentation rate or environmental parameters such as precipitation or wind current direction that can influence the atmospheric deposition of cesium.
While fallout radionuclides obviously have negative health implications, they can and have been used to track soil erosion because they are particle reactive and bind strongly to soil. The radionuclide widely used for this, for example, is cesium-137. The problem, however, is that over 60 years since the peak of the nuclear weapons testing in the 1960s, cesium-137 has undergone 2 half-lives and is now depleted and hard to detect, and only few reliable reference soils can be identified due to widespread land degradation and agricultural expansion. So now we're trying to remedy this problem by also developing further the use of plutonium for soil erosion assessment and creating a baseline map of fallout radionuclides, which could supplement or even substitute actual reference soils and has applications beyond soil erosion assessment. We scanned thousands of published research, including journal articles, United Nations reports, declassified military archives, and even got in touch with scientists to build a database of cesium and plutonium data in reference soils and to know which areas lack data. Using the ratio of plutonium-240 to 239, we also identified the sources of fallout radionuclides in the Southern Hemisphere, and we found out that the French fallout had a significant contribution around 30 degrees south in South America, which is slightly just below the latitude where the nuclear weapons testing in the French Polynesia were conducted. We also found out that in Australia, the significant contribution of the British fallout can be observed in the areas around and in between the testing sites in Emu, Maralinga, and Montebello Islands. Finally, in the sub-Saharan Africa, fallout radionuclides deposited in soils were only characteristic of the global fallout, which is a result of the nuclear weapons testing done by the US and the former Soviet Union.
As the study area of our project is covering the whole Southern Hemisphere, we are setting up a participatory network approach. Many researchers are already involved in this network, sharing unpublished data, contributing samples as we are looking for reference soils and lake sediment cores, and they are also helping us with field campaigns and samplings. This will hopefully get the fallout radionuclide community cooperating together in order to have a better understanding of the impact of soil erosion.
Beyond getting the research community together, we have future aims, of course. We want to do further field trips and sampling. We want to analyze soils and sediments from the Southern Hemisphere to fill the data gaps. But we also aim at modeled soil erosion in 2 large South American catchments and refine the sediment dating. Thank you for listening.